welcome to this episode. I'm going to look at the chapter 7 of this special publication of SAG. It's a very interesting article about magma fertility. When it comes to exploration, most explorers would stop at surface clues like rock textures, geochemical anomalies, geophysical anomalies, or maybe drill core assays, but this team went deeper. They went into the microscopic world of sulfide inclusions locked inside early magmatic minerals. Think of it like cracking open a time capsule. These tiny sulfide droplets, frozen within hornblende and pyroxene, preserve a chemical fingerprint of the magma as it was forming miles beneath the surface. And here's the interesting part. Instead of just looking at major elements like other studies, in this study they decoded sulfide signals, subtle changes like copper-rich inclusions, unusual bismuth tellurium signatures, and even the oxidation state of sulfur. And they could reconstruct the exact conditions of crystallization. So by combining thermobarometry, oxybarometry, and inclusion chemistry, they turned what used to be academic curiosities into practical exploration tools. Here's a general map of the study area. In the late Miocene, volcanic activity in the southern central Andes migrated east because of slab shallowing. It was around 27 degrees south, and this gave rise to Rincón-Portezuelo de la Ánimas field, just 75 kilometers from massive Bajo de la Lumbrera Porphyry copper to gold deposit. And here's the focus of this paper. We have two volcanic complexes which are the same age, but one of them is mineralized and world-class porphyry, and the other is practically barren. So the question is, what's happening beneath the surface? What makes one volcano copper factory and another just quiet bystander? So these two volcanic centers have a different fate. Rincón-Portezuelo's chemical signature shows typical arc-related traits like low titanium, high tantalum, and barium-niobium ratios, and SiO2% of 52 to 63%. They all suggest a classic subduction environment, but there is no significant mineralization. And so the question is that could it be a case of missing plumbing? Was there no sustained magmatic hydrothermal system beneath Rincón-Portezuelo, or the tectonic dismemberment and rapid uplift disrupt fluid focusing and metal deposition? As the subduction of Juan Fernandez Ridge led to a flat slab and reduced asthenospheric wedge, volcanic activity ceased in the arc, but some deep-sourced magmatism continued in the back arc. That could be the secret source for Lumbrera deep magmas with access to volatile-rich reservoirs and right structural traps. This study analyzed sulfide inclusions, which are, as I said, tiny metallic plebs trapped in crystals like hornblende and pyroxene. 3 types of magmatic sulfide inclusions were identified in this study. Type 1, which are copper-rich, polygonal, often unmixed, and found mainly in hornblende-rich enclaves. Type 2, which are rounded, iron-rich, with lower copper and common in late-stage lavas. And type 3, which are rare, unmixed, copper-nickel sulfides. So what do these inclusions tell us? In type A, sulfides had high copper, lead, silver, and bismuth, and that's a rich cocktail, but these metals got locked up in sulfide liquids during early magma crystallization. It means that they were removed from the silicate melt before hydrothermal fluids could carry them into ore zones. So in simple words, the magma was metal rich, but it exhaled too early. It's just like a singer who hits their high notes off stage. Here are the BSE images of melt inclusions. We have early entrapment in mafic silicates. These inclusions are found in hornblende and pyroxene, which crystallize early from a mafic intermediate melt. And this contrasts with porphyry systems where sulfides mainly precipitate late, associated with coarse veinlets and hydrothermal fluids, and they're usually not trapped in early formed silicates. And then we have diverse metal-rich phases, which are inclusions contain copper-rich, lead-rich, nickel-rich, and purtite phases. We have porphyry inclusions often show chalcopyrite, bornite, magnetite combos, but they usually have little lead or nickel at early magmatic stages. We have the presence of nickel sulfide and copper nickel phases in a single inclusion in figure H. And it's especially rare in porphyries. It indicates that there were high temperature, reduced sulfur saturation conditions in a mafic system. And we have primary sulfide saturation inclusions. They likely represent sulfide immiscibility in the melt. For example, magma became saturated with sulfide liquid before exsolution of hydrothermal fluids. But in contrast, porphyry systems often avoid early sulfide saturation because it can strip copper and gold from the melt too soon and too early. We have evidence of sulfide mixing in figures D and H. We have multiple sulfide phases in one inclusion. It suggests possible mingling of sulfide liquids or sequential exsolution events. So what it suggests geochemically, these inclusions and studies of these inclusions, it shows that they are likely formed in a deep mafic magma chamber with high sulfur and chalcophile element content. We have the presence of lead-rich and nickel-rich phases which show crustal contamination or high pressure sulfide saturation, which are typically avoided in porphyry evolution models to preserve metal fertility. In these plots, we have trace element concentrations in magmatic sulfide inclusions or MSIs. In panel A, we have lots of overlapping points and variation among vanadium, iron, copper, molybdenum, and gold. Each point is a single inclusion. They could be either type 1 or type B. And the spread, it tells us there was a real chemical diversity in the magmatic system. Some inclusions are copper rich, others show elevated bismuth, lead, or selenium, hinting at localized differences in sulfur saturation, temperature, or metal partitioning. In panel B, we have mean values, and when you compare them with compare it with panel A, you can see clear trend lines. And in these average concentrations, what stands out is that copper, nickel, and cobalt and iron dominate as expected in early sulfide liquids, but you can also see enrichments in bismuth, lead, and tellurium, which are classic late chalcophile elements and usually mobilized in fluid-rich systems. And then in panel C, we have those elements normalized to copper to show the relative affinity of trace elements for sulfide compared to affinity of copper. And you can see that in type 2 inclusions, the black ones, they are richer in gold, bismuth, tellurium, and lead than type 1 gray dots, even when scaled to copper. And this means that they held on to more of the precious and pathfinder elements, those that matter in our systems. So these patterns show a zoned sulfide system with type 1 inclusions representing an early copper dominant stage, and type 2 inclusions reflecting later metal enriched conditions, possibly linked to evolving melt composition or vapor saturation. And it's a kind of transition from a barren to a potentially ore forming environment. So while Rincón-Portezuelo didn't form a massive ore deposit like Farolo Negro, its sulfide inclusions hint that the system had potential, especially in the late stages. Here is the summary of the results of this study. First of all, we have temperature. These magmas crystallize at nearly 1000 degrees Celsius in the range of 950 to 1130 centigrade degrees. We have two samples of PA 14 and 20, which stood out as the hottest. That likely means they came from deeper or more evolved magma pulses or injections of fresh heat and material into the system. And then we have pressure results. You can see crystallization happened between 240 to 630 megapascals, which are equivalent to being blocked away 9 to 23 kilometers beneath the surface. Sample PA20 seems to have formed around 515 megapascals, which is they're related to depths like mid-crustal magma chamber, which is a classic staging ground for porphyry systems. Sorry. And what about the redox conditions? the oxygen fugacity. That's basically how oxidizing the magma was, and it came out between minus 9.7 to minus 9.1 log units, right around the NNO buffer, and that's moderately oxidized, and exactly that kind of chemistry that helps transport copper and gold in sulfate complexes. And then there's sulfur. The system carried plenty of it. You can see that sulfur fugacity values are range between 124 to 174, and combined with a high proportion of oxidized sulfur species with S6+ and S total ratios, which are up to 0.67. In simple terms, these were sulfur-rich oxidized magmas and perfectly tuned for porphyry mineralization. So, what's the bottom line? The Rincón-Portezuelo magmas were hot. They were moderately oxidized and parked in the mid-crust. Chemically, they had everything needed to drive a porphyry copper-gold system. But here's the catch. Without continuous magma recharge or the right structural plumbing, that potential may never have been fully realized. The chemistry was there, but the architecture and longevity of the system ultimately decided whether metals concentrate into an economic deposit. And that's a great reminder for explorers. It's not just about favorable magmas, it's also about whether the system kept breathing and whether the crust provided the right pathways to focus those metals. Here's another map. I took it from a different article by Amirati and colleagues, 2015. It's based on a study or a project called Siembra, Seismic Investigation of the Eastern Margin of the Andean Range. It shows the general map, including the study area, and it shows the thickness and mechanism of tectonics of this area. We are in the western Sierra Pampeanas of Argentina, and we have two major structures which meet each other. We have Tucumán transfer zone and Kalampaha alignment. This intersection happens right at the eastern edge of Pampean flat slab, and that changes everything. Here, the subducting Nazca plate flattens out, basically lying flat against the base of the continent. And that may not sound like a big deal, but it literally shuts off the hot mantle wedge that normally feeds magma into the crust. So less heat, less melt, and fewer magmas rising up, and that matters a lot. We have crust here, which is thick, which is usually great for trapping metals like copper and gold in sulfides, but that only works if there's a steady supply of magma to deliver them, and here there wasn't. Thermobarometry data shows the magma were hot and moderately oxidized, but they didn't hang around long enough to evolve into something ore forming. And compare that to Farol Negro, just a bit to the west. There the magma's magmatic system stayed active for much longer period of time. It had time to build up a reservoir mixed with different melts, and eventually formed the Bajo de la Lumbrera deposit, which is a monster porphyry copper gold system. You can see the yellow triangles in this map. They're part of the Siembra seismic array used to map crustal thickness and slab geometry. And you can see the black lines. They show the depths of subducting slab. They're not deep angle. And so what's the big takeaway here? The thick crust and the metal-rich melt are not enough for creating a deposit. Without a deep, long-lived magmatic engine and the right structures to guide it, you don't get an ore deposit. And it's a story which is written in sulfide inclusions and frozen magma. Okay, here is exploration takeaways from this study. First of all, geochemistry is telling. We see early stage magmatic sulfide inclusions reaching copper, bismuth, lead, and tellurium, and moderately oxidized sulfur signatures. Those are classic ingredients of a fertile magma, but they're not enough on their own. And second, we have thermobarometry and oxybarometry. They show crystallization in a mid-crustal setting around 10 to 23 kilometer depths and at temperatures just below 1150 centigrade degrees. Redox conditions are near the NNO buffer, nickel-nickel oxygen buffer, which supports metal mobility, but there is no sign of the kind of remelting or volatile overprinting which you need to mobilize and concentrate metals into an ore body. The third is that the tectonic context and tectonic setting matters. These are sat above a flat slab, which blocked deep mantle inputs. There was thick crust, great for trapping metals, but the magmatic system didn't persist long enough. No deep reservoir, no real fluid overprint, and ultimately no ore. So what does it mean for exploration? It means that even barren arcs can be useful. They might have fertilized the crust and leaving behind trace element and trace metal enrichments that future systems could trap into. And we should be looking into not just for metal-rich sulfides, but for signs that those metals were remobilized. Signs like hydrothermal overprints or resorption textures or hybrid magma events. In other words, copper-rich mushes are just the start, and the real clue is how they were reworked or not. Thanks for watching.